So now we're going to do a quick statics problem with springs. So it looks like something that might be on the exam, but it won't be on the exam, because it's got a spring in it. Okay, statics. And it's not a real hard problem. Okay? I know, I just do the easy ones. Right, so here's one of these ramps you have to deal with here. Oh, bad. It's at 45 degrees, which makes the angles hard to figure out. So let's draw it at a lower angle. Right, and at the bottom is like a block holding a spring like this. And pushing against the spring is the mass. That. And it's all frictionless. There's no friction. No friction. All right. Okay. So the question is, what is the compression of the spring? That's really all we need to know to figure out how much the spring is compressed, except of course there's a spring constant. So before the mass was against it, it was clearly longer, and it got shorter. Okay. So let's start with the thing causing all the trouble here. The whole source of the problem is the mass. Okay. So we'll do a free body diagram with mass. Okay. So this is the part, like the exam, you should be able to think your way through a free body diagram in this case. There's the weight pulling it down, always. mg on this side. What else going on? There's the normal force that keeps it from falling through the ramp. That's that. And now we have spring force, which you got to draw on there. Now, which way is it in your mind? Think about which way it is. It's got to be, I hope he said that way, for two reasons. We call it FS. One reason is we displaced or we've compressed the spring this way, delta x is this way, so the force has to be that way. The other reason this is statics. If I drew this force this way, it's going to be hard to balance the forces in x and have it be still. Right? It has to be that way so that we have some shot in balancing those x forces. And then in this problem, if you're doing this in the exam without the spring, you would probably be better served to work in coordinates like this, right? A perpendicular direction and a parallel direction like that. That would be better, because then we just have to convert the mg, those coordinates, rather than converting two forces in and fs to regular Cartesian. And then maybe you've done this so much now you don't have to write it, just do the detailed trig again, but you know that you could break mg into components like that, and you know that theta would be there. So the one pulling it down the ramp is mg sine theta. That's opposite of the angle, and the one pushing it into the ramp is mg cosine theta. How else could you check that? You can think about small theta. What if theta was 0? If all the weight was pushed into the ground? Does that make sense? If theta was 0, how much acceleration would it have along the ramp? None, because it's flat. So I would like to use those limiting cases to help me think about these things, because I'm not very it helps me. So now we'll do some of the forces in the perpendicular and some of the forces in the parallel. So let's go over here and do that. So some of the forces in the perpendicular direction. So you look at it and you say, perpendicular, you have n is up. We're just writing magnitudes here. So I'm going to put a positive sign in front of it to make it up. Except I'm not, so the positive sign is implied. And then I've got mg cosine theta down. Magnitude, magnitude, magnitude. I put the negative sign in. And it's a statics problem, so that has to equal 0. So basically, as we've seen in these problems before, in this case, the normal force is mg cosine theta. Sorry, what does a delta x say for the number? That just says 0, positive, and negative, if that's what you're talking about. It's not a number, I'm just saying. Let's see, so that's perpendicular, and then let's do some of the forces in the parallel direction is, let's see, the positive direction is the spring force, Fs. And then the now negative direction is minus mg sine. That has to be 0. What are we trying to do? We were asked the compression of the spring. How much is the spring going to get pushed? So we know that's hiding in here. Right? So what we'll do is we'll solve this one. We'll say, okay, the spring force equals mg sine theta. We don't really need the vertical information, so it's not a friction problem. Hold on. And then we'll say, well, that simply equals minus k and whatever delta x is. Because this is Hooke's law. Fs equals minus k delta x. Okay? So I didn't put the negative sign here because it's a magnitude and it's positive. But then this negative sign is actually in the law. Okay? Constants are negative, but sometimes physical laws have a negative sign in them. It means go the other way. There's not too many. This is one. Okay? Hooke's law. That's a case where you do always put the negative in, and now you can see what's going to happen. Delta x is negative mg sine theta over k. There we go. And negative, what does negative mean? Oh, negative, good. It means it compressed the spring. So, good news. I've got a good question. I'm glad y'all are taking the artistic part seriously. Remember I told you how much of a better drawer, is that a word, you're going to be by the end of the semester? Some of you are taking it seriously. You want to know, how do you show that the spring is compressed or stretched in your drawings? That's the best I can do. You should put the little loops closer together. So don't get too carried away with your drawings. But yeah, there's no technical meaning to how dense you draw the loop, because all springs are different. Okay? So that was a statics problem. And yes, that was not like a really hard pledge kind of problem. We're just getting started. Oh yeah, and somebody here is asking, what if I use 270 plus theta? So here is an example where I didn't do the big formal mathematical method, did I? No. I didn't even say if I was doing this as positive theta or negative theta. I'm tired of doing that. It's just that component, and I'll make it negative. But yeah, we could have formally said theta equals 0 is here. I must go 270 plus theta and put that into Google to figure out what that sign becomes. You can do that. But I'm just kind of doing it the shortcut. We did it the long cut way for on. Okay. Who wants to do a dynamics problem? I'm going to give it to you. Okay. That sounded like a yes. I need people to be brave, okay? Why does it say Fs if there's no friction? I'm sorry, I was using S for spring. That was a spring force. I shouldn't have used S, right? Because that's normally friction. That was a spring force.